Hello, my name is Miguel Saavedra.
And my name is Sacha Morin. Today we'll be presenting our IROS paper, One-4-All, Neural Potential Fields for Embodied Navigation. So this paper is about visual navigation. So we have an agent or robot that needs to reach a goal using only RGB camera images. The goal is also specified as the goal image you need to reach. The paper is also about topological navigation. That means we want to navigate the environment without explicitly building a metric map. We achieve this by driving the robot around in order to collect images, and then we build a graph where the nodes are the images and the edges encode some notion of reachability or proximity. How do you use such a system? You first localize your robot in the graph using some image retrieval algorithm, often using a neural network. You do the same with the goal image, and then you can run an algorithm such as Dijkstra to figure out a path. You can then rely on the low-level controller to travel from node to node until you reach the goal. What are the pros of topological navigation? You can achieve long horizon navigation in complex environments, which remains a challenge for end-to-end learning method. And it also works surprisingly well using only RGB inputs, which could be challenging for existing classical methods. Now, in terms of the cons, there are some scaling issues. So when you're facing large environments, you need to collect a high number of images in order to represent your environment well. Also, to keep graph queries reasonably fast at runtime, you need to tune a number of heuristics with a lot of hyperparameters to make sure that things remain reasonably fast. So our method, in short, we basically want to get rid of the graph. And in order to do so, we train a neural network to implicitly encode the geometry of the graph. More on that later. So the final system is fully parametric and only relies on neural network inference. In terms of sensors, we use two cameras. We use a front laser scanner only during navigation to detect collisions. We don't use the laser scanner during training. We do not use other depth sensors, and the pose is not observed. We do not estimate the state of the robot. In terms of actions, we have a discrete action space. The first action is stop. The robot needs to autonomously call stop near the goal. We also have the forward, rotate right, and rotate left actions.
Okay, to present the system, it is basically composed of 4 modules. The first one is the RGB backbone, which learns to predict image embeddings using contrastive learning. The second component is the inverse kinematic. This predicts pairwise connectivity between any pair of images. Connectivity here implies is that one image is reachable from one another if we can get to it within one single action. Note also that the inverse kinematics model is used to construct a directed graph. For the forward kinematics is the third model, and this learns to predict image embeddings given the current embedding and an action. And lastly, the geodesic regressor learns to predict shortest path lengths between any pair of images. As a whole, the system looks like this. By following the arrows, you can see how all the pieces are tied together. But during deployment or navigation, which is the interesting part, we discard both the directed graph and the inverse kinematics model. Now, how it works is we take a goal image and the current image being observed by the agent. We encode this with the RGB backbone, and then we take all the possible actions and produce waypoints using the forward kinematics model. Now, we pick the best waypoint, which is ranked thankfully to the geodesic regressor. The geodesic regressor here is being used as a component within a potential function, specifically as a positive component. There is also a negative component in the potential function, which is produced by the previously visited states. It is very important to note that this is just an example in 2D, but our potential function lives within a highly dimensional embedding space. Now, for the results, we compare against the state-of-the-art methods, both parametric and semi-parametric. As you can see here, we use as metrics the success rate and the optimal path length, or SPL, and overall, our method excels in comparison to all the other baselines. Interestingly, even though our method did not use any pose information, the unsupervised latent geometry is consistent with the actual ground truth geometry of the environment, as you can see. Now, we also deploy the system in a real-world laboratory. In the bottom right, you can see the goal image, and the bottom, you can see the current image being perceived by the agent. And basically, our system is capable to reach the goal seamlessly, and it autonomously calls stop as soon as it reaches the goal image. Thank you very much for attending our presentation.